So the rate of change is the ratio of the change in the output to the change in the input. And that formula right there should look familiar. It's actually the slope formula. That I believe we talked about the first week from algebra. That's just the slope formula. So the average rate of change from one x value to another is just simply the slope of the line between those 2 points. So we have an example of a graph that shows the number of units in some commodities sold when X $1,000 are spent on advertising. So it says find the average rate of change of N as X changes from 1 to 2, from 2 to 3, 3 to 4. We may not do all of those, but just get an idea. Okay, so from 1 to 2, we're looking, we're just basically looking at the slope. It looks like that first point is 1, 1, and the second point is 2, 300. All right, so the average rate of change will be like I said, the slope formula, the second y minus the first y divided by the second x minus the first x, and that's just 299 over 1, which is 299. Okay, give a room here. My computer is being really unresponsive. It won't let me bring up the keyboard. All right, well, it's doing something in the background. Okay, from 2 to 3. All right, so that would be between, or display between the points 2, 300 and 3, 480. And again, the average rate of change for those 2 points would be 480 minus 300 divided by 3 minus 2, and that's 180. And I guess maybe let's do one more round. From 3 to 4. All right, again, the point 3, 480, going up to the point 4, 600. Average rate of change is, let me get the keyboard. Oh, I don't know what's going on. All right, so that'll be 600 minus 480 divided by 4 minus 3, and that is 120. All right, so let's go back and look up at the graph. The little blue line, we're saying that the slope of that line, which is the average rate of change between the 2 points on the curve, the slope there is 299. For the little yellow segment, the slope is 180. For the little green segment, the slope is 120. So then it says, why do you think the average rates of change are decreasing as X? So as we go from the first point to the second point, second to the third, third to the fourth, and so on, the slopes are decreasing says, why do you think the average rates of change are decreasing as X increases? Well, you may or may not have an idea of that. But the reason is, and it's a little hard to see, that the actual graph is a curve. It's that thinner black line or curve, sorry, that represents the function. And so the function n, how do you think the average rates of change? Well, that's actually a pretty loaded question. Why do you think they are? Because that's kind of a topic we will study later. But it turns out that the function is actually increasing at a decreasing rate. Or another way to say that would be that it's slowing down. All right. Okay. So the slopes themselves are decreasing, and hopefully you can just see that from the calculations. All right. Okay, the next example, you're given the equation of a function, and it says find the average rate of change as X changes from -2 to 0, and then as X changes from 1 to 3. Okay, so this time we need to compute our function values. Well, I'm a fan of using the calculator to help me out here. So I know you can't see what I'm doing here, but I'm going to post a screenshot. Okay. So here's, all right, there's where I just entered the function in for y1. And what I'm going to do is use my table to look at the X values that I'm interested in parts A and B are -2, 0, 1, and 3. So I'm going to my table and putting in -2, 0, 1, and 3. Let me know if you want to see the actual calculator screen or the actual calculator. This is the screen. Okay. So if you remember, I had you set up your table so that you can type in specific values that you want for X by putting X on Ask and Y on Auto. All right, so as X changes from -2 to 0, the average rate of change will be the slope of the line through the 2 points, -2, -2, and 0, 0. All right. So you can call it M if you want for slope. All right, so the second Y minus the first Y divided by the second X minus the first X. The double negative becomes positive, so that's 1 or 2 divided by 2, which is 1. All right, so the average rate of change for those 2 points would be 1. Then for part B, we've got Point 1, -2, and I think it's 318. Yeah. So as x changes from 1 to 3, the average rate of change, again, is the slope of the line between those points. So the second y minus the first y divided by second x minus the first x. So that's 18 plus 2, which is 20. 3 minus 1 is 2. And then 20 divided by 2 is 10. Okay. And that's it. What I might do, just get my voice going. Might just bring up the calculator, the graph of this function. Let me get that fixed up for just a second. Kind of, again, show this from the graphical standpoint. All right, here's a picture of the graph of that function. Okay, initially in part A, we were asked to find the average rate of change as x goes from -2 to 0, right? -2, yeah, so -2, -2, -2 is right here, 0, 0 is right here. And what we found was the average rate of change is actually the slope of the little red line that I just called, or that I just drew. It's called the secant line. Somewhere I'm going to be mentioning this, okay? But this is called a secant line. And its slope is the average rate of change of that function between the 2 points. All right, average rate of change from x equals -2, x equals 0. And then in part B, in part B, we went from x equals 1, which is right here, to where x is 3, and that's somewhere here. So the slope of that line is 10. All right. So slope of that line is 10, which is the average rate of change. So the average rate of change, if you look in the little information box, the average rate of change of a function with respect to x is also called the difference quotient. And if you took college algebra, you probably remember this expression. It's just a big algebraic expression. This is kind of a general formula that gives you the average rate of change for a function in general, okay? So it's that big looking, this big looking expression, and sorry, I'm trying to get my, okay. if you were taking math for STEM major, science, technology, math, engineering, we would look at this in great detail. We would be defining, I don't do that. Yesterday, my Word document started going crazy, and it looks like it might do that again. Please don't do that. Sorry, I'm trying to erase something that's not letting me. So I'm having some bad luck with my computer. It's letting me. All right, I'm just going to hope that that goes away. Sorry about that. Anyway, this difference quotient, oh, I can see it's going to be messed up. I'll probably like, what is she doing? Good question. I'm trying to make this cooperate. Okay, I think it might work now. Let's see. All right, so that's the difference quotient. And next, you see, this is the formal definition of a derivative. All right, formal definition. That the derivative of a function is found by computing that difference quotient and then computing the limit of that difference quotient as h approaches 0. And like you may remember me saying, that's why we start with limits, because a derivative is defined in terms of a limit. All right. So first of all, let me mention this notation. This is the notation for derivative. That is red. F prime of x stands for the derivative. All right. F prime of x. All right. And again, notice that it's defined in terms of a limit. So it's all of this stuff here. So what I'm going to do is just show you this definition. Okay, it's doing it again. Okay. I really don't know what's going on here, and it's very frustrating. Very frustrating. I'm sorry. All right, so I'll see if it's going to cooperate. All right, so in the next example, I'm going to use this, it's called the limit definition or the formal definition to find the derivative of the function x squared minus x plus 1. And we usually, to begin with, we break this down into some steps, 4 steps, as you can see coming up. So the first step is to find f of x plus h. And that just simply means substitute x plus h into the function substitute for x in the function. All right, so f of x plus h would look like this. X plus h squared minus x plus h plus 1. All right, then we expand that, remove the parentheses. X plus h squared is x plus h times itself. So multiplying that by FOIL gives me x squared plus, oh my gosh, my brain, x squared plus hx plus another hx plus h squared. Then I distributed negative over here, this negative. This multiplication I did by FOIL. And that's pretty much it for the first step. The second step says, okay, continue from what you did in step 1, subtract f of x. So now subtract the function, the original function. All right, so we're picking up what we got from step 1. I'm just bringing it all down here. I'm also combining the two hx's. And I'm subtracting x squared minus x plus 1. Again, because I'm subtracting a quantity, I need to distribute the negative over where I just drew those red arrows. I'm just copying everything else that I have. Now minus x squared plus x minus 1. And at this point, I should be able to combine some like terms. Right, specifically, I've got an x squared and a minus x squared that cancel out. I have a minus x and a plus x that cancel out. And I have a plus 1 and a minus 1 that cancel out. All right, after I've done all that canceling, I'm left with 2hx plus h squared minus h. The third step in this says, okay, we've now gotten the numerator of that strange looking fraction. Now we're going to divide that by h. All right, so 2hx plus h squared minus h, all divided by h. Well, the way that I actually do this, there are two ways, but generally what I do is factor out an h from the numerator so that then that's how I divide by h. I factor it out and I'm left with 2x plus h minus 1. And like I said, if you took college algebra, you did this up to this point. You said, okay, that's called the difference quotient for this function. And that was preparing you for this situation, for finding the derivative of a function. The fourth step says, okay, now take the limit of that expression as h approaches 0. So the limit as h approaches 0 of 2x plus h minus 1. Remember that for a limit, we do that by substituting. So we want the limit as h approaches 0, so we substitute 0 for h. which gives me 2x plus 0 minus 1, which is 2x minus 1. Okay. All right, so what are we saying? All of that, we're now saying, okay, that is actually the derivative of the function that we started with. That's what we were after. All right, so we say the derivative of that function that we started with way in the beginning is 2x minus 1. All right. Now, if you're like, have no idea what she just did, don't worry about it. Because in reality, we don't do this. All right, I show it to you basically because it is the definition, and you know, I like for you to have a little bit of appreciation for that. But in reality, this is not how we find derivatives. So don't freak out. In reality, by probably the next class session, if I ask you to find, if I ask you to find the derivative of that function that we started with, you would have the answer in about, depending on how often you practice, you would get the answer in about 20 seconds. All right, so it's really not, it's not going to be like this. All right. Okay, so this is where I mentioned secant line. That one's a little out of this is where I mentioned a secant line. So if you think about a circle, a secant line cuts a circle in 2 points. A tangent line touches a circle in exactly 1 point. And we can look at that same concept for any smooth curve. Below that is the curve of some function. And look at line L. All right, we're saying, we're going to say that line L is tangent to that curve at point P, even though the line crosses that curve in other places. In this, it says in this small interval. So if you just kind of say, okay, in this interval, line L is tangent to the curve at point P. It says that, but I'm writing it anyway. All right. Well, what does that have to do with anything? Well, it turns out there's a connection in calculus between the derivative and a point, that's called a point of tangency. So slope of a tangent line is what we're talking about. Okay, so the derivative of a function also gives us a formula to determine the slope of a tangent. And when we say tangent, we mean tangent line. So if you wanted to add that in there, slope of a tangent line to the graph at any given point. So basically the slope of the line is the same as, the slope of a tangent line is the same as the derivative of the function, and the slope of the tangent line at a particular point can be found by evaluating the derivative at the x coordinate. All right. And oh, there it goes again. Whee! I don't know what is happening with my computer. I don't know. Sorry. I'm just gonna leave that there because it doesn't want to cooperate. All right, so going back, that's the function we just looked at, and up in on this page, we found the derivative of the function to be so f prime of x, we found to be 2x minus 1. That was from example 3. All right. And to find the slope of the tangent line to the graph at the point -2, 7, we just simply substitute x equals -2. So the slope of the tangent line at -2, 7 is f prime of -2. So we go in and substitute -2 for x in the derivative, which is -4 minus 1, which is -5. Okay, now my dogs are going to bark. All right, so like I said, if you're kind of out in outer space right now, don't feel bad. The main thing that, like I said, the main thing that I want you to know from this, Charlie, stop. Is, that there's a complicated formal way to find a derivative. We're not going to use that formula. Okay, hold on a minute. Hang on a minute, guys. Okay, sorry. I had someone ringing the doorbell, so I had to check on that. It's quite an experience teaching from home, I tell you. Okay, so what I was trying to say was, I gave you an introduction to derivative, the complicated form version and so forth. Starting with section 1.5, you're going to be much happier because this is where I give you formulas for finding derivatives. We won't use that limit thing. You will never have to do that for me on a test. You may have to do some of it on the homework. That's fine, for practicing, but as far as, for me, we will use the formulas from now on. All right. So that's where we begin with formulas for finding some derivatives. You're going to like this a lot better, I promise. First rule is called the power rule, and it is for finding the derivative of a function that's in the form x to a power. Okay, The power can be any real number, anything, a positive, a negative, a fraction, any kind of real number. And this is the rule for the derivative. Pretty easy to use, and once you've done this several times, it's very easy to use. So for finding the derivative of x to a power, a function that's in that form, we take the power times x and then subtract 1 from the power. All right, I'll hop right down to the first example, and show you how easy this is to use. So we write g prime of x for the derivative of g. All right, we have x to the 5. We take the 5, multiply by x to the 5 minus 1. And simplify that, it's 5x to the 4th. All right, it's pretty simple, I hope. Part B, I'll go ahead and show you that one. That's actually illustrating the quotient rule, the coefficient rule, which says, okay, suppose you have a coefficient times a function, which is what I have in part B. So it's really 6 times x to the 4. To get the derivative of that function, you just keep the 6. So you'll hear me say, hang on to the 6, and then use the power rule for the derivative of x to the 4. So that's going to be 4 times x to the 4 minus 1. All right, we can go ahead and multiply the 6 and the 4 together, and then subtract 4 minus 1 is 3, and you're done. All right. So these are both illustrations of the power rule for finding your derivative. All right, any questions so far? And in part B over here, we use the coefficient rule first, and then we use the power rule. Okay. In reality, as we start doing this, you kind of do that without thinking about it. You're like, oh yeah, keep the 6. And in fact, the 6 gets multiplied by the power of 4. For part C, all right, just remember that x really means x to the first power. So for the derivative, and we write f prime of x, we hold on to the 9 because it's a coefficient. We multiply the power, which is 1, times x to the power minus 1. All right, we multiply the 9 and the 1 is 9. 1 minus 1 is 0. So we have x to the 0. Well, because we're dealing with powers and exponents, a lot of rules from exponents come back into the picture. And it's actually a definition that any number to the 0 power is 1, except for 0 itself, but that won't ever come up. Okay. So x to the 0 becomes 1, 9 times 1 is 9. All right. For part D, that is the constant function rule up here. Okay, if you remember, we had a special rule for the limit of a constant. Well, we have a special rule for the derivative of a constant. There it is. The derivative of a constant is 0. Derivative of a constant is 0. So for part D, 6 is a constant, or this is a constant function. The derivative of a constant is 0. Plain and simple. Okay. Okay, let's do part E. If you have a question, let me know. Let me see where I am. For part E, all right, let me just back up for a minute. Here's the thing you have to be cautious about with using the power rule. In order to use the power rule, the function must have the form that you see right there, which is x to a power, okay? So x to the power cannot be in a denominator. Or under a radical. All right, so what do we do if it's not in that form? Well, we have to rewrite it using the rules for exponents. The function in part E, you're like, well, gosh, that looks different. Okay, it looks different because the exponent is negative, but we don't care. It has the form f of x equals x to a power. It's good to go. Now, if you look over at part F, that one is not. So we'll look at that one in a minute. So for part E, we just use the rule the way it stands. We take the power, which is -3, multiplied by x raised to the power -1. You're always subtracting 1 from the power. Okay. All right. So if I actually subtract 1, -3 minus 1 is -4, and that's going to be the answer. Okay, that's it. Now, again, depending on your algebra background, you may have been taught, well, you shouldn't leave an answer with a negative number. I'm sorry, a negative exponent. I'm sorry, I've got some distractions going on here. But we're okay. Here is what we're going to do. And I say it's our rule. It's my rule. And the book, typically they're going to tell you how to write the answer. But for me, you can always do this. And that is, we're gonna leave the answer in the form of the original function or problem. Leave the answer in the form of the original problem. So if my original problem has a negative exponent, like this one does, then it's going to be okay to leave the answer with a negative exponent. So we're done. We don't have to do anything else for this one. All right. For part F, okay, this is not in the form we need. Why not? Because x is in the denominator. All right. We have to rewrite before we ever use any derivative rules. We have to rewrite the problem using, again, this definition from exponents, that 1 divided by x to the n means x to the negative n. All right, this is another definition from exponents that you have to use in calculus to go back and forth from one form to another. All right, so for 2 over x squared, that's the same as 2 times 1 over x squared. And then 1 over x squared is 2 to the negative 2, 2x to the negative 2. Now we can use our power rule. Yeah, my dog's going to start barking. Stop, 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 stop. All right, so I'm going to keep the 2, which is the coefficient, multiply by the power of negative 2, keep the x, and subtract 1 from the power. That's what it looks like. 2 times negative 2 is negative 4. And then negative 2 minus 1 is negative 3. Now the rule is, okay, my original problem did not have a negative exponent. So in this case, I'm going to need to rewrite this with a positive exponent. So here we go, keep the negative 4. X to the negative 3 means 1 divided by x cubed. And then multiplying those together, I get negative 4 over x cubed. All right. All right, let me see. All right, let's do the next 2, and then I'm probably going to stop for today. I've got stuff going on here that's, I'm afraid I'm not going to be able to keep my dogs from going crazy. Also, it's a lot of stuff that I've talked about, and I want you to be able to think about it some. For part G, notice that it's in the form we need, x to a power. Remember, that power can be any kind of real number. So it's ready to go to use the power rule. For g prime of x, I'll take 2/3, which is the power, times x to the 2/3 minus 1. All right, well, 2/3 minus 1, need a common denominator. So I think of 1 as 3/3. 2/3 minus 3/3 is negative 1/3. That's kind of my scratch work, or you could use your calculator. So that's 2/3 times x to the negative 1/3. And that's the derivative. And it would be okay, except the original problem doesn't have a negative exponent. So again, I need to rewrite my answer with a positive exponent. Hang on to the 2/3. X to the negative 1/3 means 1 divided by x to the positive 1/3. And then you can multiply those together, the numerators together and the denominators together. And that is your answer. All right. Any questions? Oh, it's a lot. Okay, for part H, that's not the form we want. It's got the x and a radical. So now we have to use again, these are definitions from the world of exponents. In general, the square root of x is x to the 1/2. The cube root of x is x to the 1/3, and so on. And then in general, sometimes you might have something like this. The little n is called the root of the radical, so it's the nth root of x to the m. Actually, let me back up for a minute. It's not going to let me do that. Yes, this. Okay. In general, the nth root of x is x to the 1 divided by n. And then you may have, under the radical, you may have a power. So these are the rules in general. The nth root of x is x to the 1 divided by m. And the nth root of x to the m is x raised to the m divided by n. So back to my problem. The first thing I have to do is rewrite my function. The square root of x is the same as x to the 1/2. Now we can use the power rule. For the derivative, keep the 1/2 or multiply by the 1/2. Take x to the 1/2 minus 1. All right, well, 1/2 minus 1 is negative 1/2. Now we've got something similar to what we had in the previous problem. X to the negative 1/2 is the same as 1 divided by x to the 1/2. And then to this is what it looks like if I multiply the fractions together. And then finally, it's a lot of work here, but finally, because the original problem had a radical, I'm going to write the answer using a radical. So we start with a radical, we have to change it to an exponent, we use our derivative formula, then we change it back to a positive exponent and then back to a radical. All right. So, and you're probably seeing this here, but a lot of times in calculus, the algebra is messier than the calculus. That is true, okay, which is why a good algebra background is very useful in a calculus course. I try not to stress problems like this one, okay, because you all are not STEM majors and we are more interested in applications where calculus would be used. So like I said, I tend not to stress these. I just have to show you all the different things that can happen. So again, don't get too anxious about it. I try not to put very much with radicals on the test. All right, that makes you feel better. Let me see where I am. So I want to be able to finish everything between today and Thursday. Does anyone have a question yet at this point? All right, I'm going to just go ahead and talk about the derivative of a sum or a difference, and then I will stop after this one. This is not hard either. We are talking about the sum rule. The sum rule is the rule for finding the derivative of a sum of functions, or it could be a difference of functions. So the two examples that you see, this is what we're talking about. In part A, that's x squared is a function, plus 4x is a function, minus x. There's three functions there that are added together. All right. So the sum rule says you just get each derivative separately and take their sums. So this is how I'm going to write it. And this is sort of what's the word I want? It's kind of like the abbreviated notation. I'll talk some more about notation next time. But I'm saying, hey, get the derivative of x squared plus the derivative of 4x minus the derivative of x cubed. So you just compute the derivatives separately. All right. So for x squared, that's 2 times x to the 2 minus 1. Remember 4x, that's 4x to the first. The derivative is 4 times 1 times x to the 1 minus 1. And then for x cubed, it's 3 times x to the 3 minus 1. And then keep going. That's 2x to the 1 plus 4x to the 0 minus 3x squared. X to the first power is just x. Remember, x to the 0 is 1. So we have 4 times 1, which is just 4. And that's the derivative. Okay. All right, I'm going to leave part B. And we'll start with that next time to kind of review a little bit. Anyone have a question before we sign off for the day?
No, ma'am.
Thank you. Anyone else? Are you finding it helpful to have the recordings available?
Yes, ma'am.
Yes?
Yes, ma'am. I am.
Okay. No, I never really know how many people are actually paying attention. And it's fine. I mean, you may rather sit down and watch it on your own where you can pause it and stuff. That's fine. It doesn't bother me. All All right, well, I'll go ahead and stop the recording and